Good morning. Welcome to episode number 57 of the Zoomtown experiment. Last week we talked about steering the Zoomie in reverse. And in that episode I explained to you a little bit about how the motion processing is performed within the Zoomie, the new Zoomie control program. And today we're going to take a look at all of the different motions or trip instructions so that you get a better understanding of what capabilities it has and how it performs those. I'm going to try to keep this as brief as I can, but there is a lot of information that we're going to cover in this video. Let's start out by looking at an outline of what we're going to talk about today. Now, in the past, you might recall me referring to the trip plan, and that's really what we've got going here, but I changed the wording to trip instructions to help my mind catch up with the new program and not keep living in the old program. Sorry about that if it adds a little extra confusion to the process. But here we go. We're looking at our trip instructions. Now, the non-motion trip instructions are really quite simple. We've got BEG for the beginning of the trip instructions, and that would be the first command in the entire list. End would be the last of the trip instructions on the entire list. The trip instructions are stored in a Python list. The WAT command, it tells the scheduler that the Zoomie is waiting for the OK to proceed, usually when the Zoomie is at a stop sign or perhaps was interrupted for some other reason. STP is simply a stop instruction, meaning that the Zoomie will not be making any motion at this point, and it will come and ensure that it is at a complete stop. DWL is our dwell, and that is a non-blocking trip instruction. Now, if you can imagine a dwell, the equivalent in Python would be a sleep for X number of time. Problem with sleep is it's blocking. Nothing else can happen. Where in the case of this dwell command, I can tell motion to stop, but all other activities to continue. Moving on to the trip instructions that cause motion, we've got CAD and RTN. Those two work together. CAD is check for address, and that would be when the Zoomie is in a driveway. What it'll do is it'll look for the QR code in the driveway by backing up a few inches. That'll give the QR code scanner an opportunity to scan the QR code, at which point then it will return to the repark position or the park position within the driveway. So those two functions are always handled one after the other. Park, PRK, and unpark, UPK, those two commands allow the Zoomie to pull into a driveway, read the QR code while it's doing it, and park at a very specific location. It's essentially a 1/4 inch wide marking tape that goes across the guideline. Unpark will back out of the driveway, and it is now using our new bang-bang steering method so that it stays nice and straight when it is backing out of the driveway. And it will use just QR codes, it'll use just encoder feedback to determine how far to back up. PUP is a pull-up maneuver, and that is where you would be in a situation where, say, you're at a stop sign and you're going to turn into traffic, either left or right. You have to pull forward a little bit before you make the turn. So that is what the purpose of PUP is, to get you across the traffic lanes to prepare for a turn, to go in the correct heading. PVT is my pivot turns. This is very similar to what we had in the past, but it's all combined into one class method for both forward, reverse, left, and right. That type of motion is strictly turning by rotating one of the two wheels and pivoting on the non-rotating wheel. SWT is the sweep motions, or the sweep turn motions. And that can go in both directions, either right or left. In our case, on the Zoomtown layout, all left-hand sweep turns are the large radius, right-hand sweep turns are the smaller radius turns. The sweep turn is also changed within how I'm handling it. In the past, it would stop before the next or adjacent road, so it'd stop right at the start of the road. Right now, I've modified that so the sweep turn actually ends within 1 inch or about 25 millimeters into or past the start of the road. And that helps solve a few more positional errors I was experiencing. And finally, we've got CRS, which is short for cruise, and that is normal road driving. And during that motion, you're going to see a lot of input from sensors. You'll have zero set, preset, QR code reading and setting of position, as well as line follow steering in the forward direction. That's really the workhorse method of all the motions. That does not diminish how difficult each one of these is in order to get them to perform as accurately as I think they need to be for this experiment to move forward. The trip instruction parameters are very similar to what we've had in the past on the previous version. We'll have 10 parameters that define all the items needed for that motion to be performed. And it would look very similar to that particular command, which is a cruise command. So let's break it down parameter by parameter. CRS is the motion type, which is a cruise in this example. The next two numerical values, 87.5 and 46.0, are the absolute coordinate to move to. That's a huge deviation from our previous methodology where I was strictly going by distance. In this case, that is the coordinate I want to move the Zoomie to within the Zoomtown city limits per se, with the upper left-hand corner, or the far left-hand corner, being 0, and all other positions coming off of that. Y plus coming towards us, and X plus going to the right. Some moves still require a distance to be specified for how far to travel, such as when we're checking the QR code in the driveway, backing out of the driveway. Parking and unparking is often done by distance, not position. Sweeping turns are done by distance, but they have an associated component of that with an actual absolute coordinate relative to the Zoomtown layout. Turn direction, in this case, we're just cruising, so there is no direction needed, so it's got just 3 dash marks, but otherwise it would have left or right in that location. The direction is traveled specified with forward, FWD, or reverse, REV. The heading at the start of the motion, that is critical to help with computing distances traveled and absolute coordinates. If I know the heading and I know how far I've traveled, I can put that into absolute coordinates. And that is also communicated to the scheduler so it too can figure out where the Zoomie is going. The next parameter is 0.7 is the velocity of the motion, which is in the range of 0 to 1, representing 0% to 100% of the total velocity. Maximum velocity is about 8 somewhere between 8 and 10 inches per second, which would be about 200 to 250 millimeters per second. And then finally, we've got two more parameters, STP, which would be the next command in line. So when I'm creating the trip instructions, I have to look to see what the next motion is and record it in this location. That helps control how the Zoomie performs at the end of each individual motion. And finally, if it's a sweep turn, I have to specify the radius. That helps with computing and calculating the global position or the absolute position for both internal use and for communicating over to the scheduler. Now that we've covered what some of the trip instructions are, let's take a look at how I process them for execution per se. Now at this phase of testing, remember this is a full rewrite, so I'm still in the testing phase. I am not getting the trip instructions from the scheduler. I'm actually creating them locally within the Zoomie control program. But at the beginning here of the program, this is the class version of it, or object-oriented programming style. And right about here is where I load in all the external libraries containing our other classes. I don't need those internal. Most of those are fairly well proven out at this point. But this is my biggest class and the one that controls a lot of the program and of course all the motions, and it's called process trip instructions, and I instantiate it with just simply PTI. We're going to have some variables that are needed and a few other methods are going to be in here in the earlier part of this, and then we'll get into the motion stuff. But we're doing a calibration routine as an experiment right now, so I won't go into that. Sometimes I like to print out the data that was coming in via the trip instruction. When we're working with the MQTT, we're going to add in the instructions via that method, and we're doing that sort of below. And from here, we'll append that to the TIL, trip instruction list. It's a basic Python list. This will clear it all out when we're all done. The executor is what executes the command to start with. Almost every trip instruction starts out with a start, and then there's a perform. The start method simply creates everything necessary for that motion to be performed. And that'll make sense in a moment here. But as we run one of the trip instructions, it will see that it's either park, unpark, pull up, and then it'll run the start method to get that particular method going, or motion going. Once we get everything going, then from the main loop we'll call process actions. If there is a command in there, such as one of these, it will then perform that action via the perform park method or whichever one. I have an initialization method that'll go through and get all the parameters set that are universal to just about every trip instruction. And from this point down, from line 469 all the way down to uh, 1038 per se, that's all the motion commands or trip instructions. Some of these I'm just going to briefly blow through just so we can keep moving at a pretty decent pace. The BEG, or begin instruction, doesn't really do much other than call the executor to run the next command. The stop function, this will stop everything and just simply communicate a message to the scheduler to let it know I'm waiting. Please send me the OK to go instruction, in which case I will then run the wait instruction until I get that message. End is another non-motion one, and that just simply ends the whole list. It's cleared out automatically as it's being read. I'll show you that here in a little bit. But any current action is then set to 3 hyphens so that when the main loop is calling this, it doesn't do anything. Our dwell function is another do-nothing one. We would start that action, and then when we perform it, we're essentially just kind of counting down on that time. Reverse calibration, that is a function that is experimental at this point, and it's going to work with what we did last episode with reverse bang-bang steering. This is to calibrate the motors so that they are very equal, and that constant would be calibrated here, recorded on the PICO in its file system, and then we would read that so that both motors run pretty close to the same speed so that the bang-bang method doesn't have to work so hard. And that's the start function for it and the perform function. Now we're going to get into the real meat and potatoes, so to speak, of our trip instructions. These are all the motion commands. And one of the new ones is for the Zoomie to, while parked in any driveway, I can just take a Zoomie, place it in a driveway in the proper place where it would be parked, and it's just an approximate. I can run this command, the Zoomie will back up, look at the QR code, and then pull forward again and park properly. And by looking at that QR code, the Zoomie knows exactly where it is. Really a handy feature. And that position is then also communicated to the scheduler so that they're both in sync. Very cool feature. I believe I talked about that as well lightly a few episodes ago. Now, let's kind of look at this because I can explain to you really well what all is happening with these start and perform functions. Here you can see I've got no presets or anything because the Zoomie is lost. It has no idea where it is. We're going to check the CAS, and that will give me a rough idea where it might be relative to a barrier or something like that. I'm going to run that initialize parameters method up above. That'll take care of getting the bulk of everything I need ready to perform a motion. We will establish what the current action is. It's perform check address, which is the same as the name of the method. Makes it easy when I'm decoding that. If there is no action, it's just simply 3 hyphens. I go through, I will adjust the run velocity for the motors, and we're going to preset a few more variables or attributes in the world and get things set the way we want it. And here I'm adjusting the target speed to the performance factor of the motors, which is working in conjunction with that calibration routine. So some of this may or may not be in the final code. Anyhow, this is what's required to perform the actual check address. This is the method that will actually perform the action or perform all the control of the motion. It'll start out with this debug print statement, which currently set to no. I've been doing this more and more, and it really helps with efficiency while debugging. That way I don't have to recreate these print statements to show the information that's pertinent to debugging this method. So if that was yes, it would print the stuff out. No, it just leaves it alone, and I don't clutter up the shell down below. I'm going to put the left and right speeds, copy those into local variables from the method variables or attributes. I'm going to set the decel rate to 0. I don't want it decelling yet. But now at this point, those are the only real preparatory things I need at the beginning of the method. From here, I'm going down all the way. This is going to perform any steering or any other control functions that I need to have performed during this motion. First one being, if the decel flag is 1, lower the velocity that you're traveling at. If the left photo switch, this is reverse motion, so we would be looking at the rear photo sensors, which are digital inputs. And so if the left one is equal to 1 and the right one is equal to 0, I want to take my left wheel speed and reduce it by 55%, or make it equal to 55% of what it used to be. And likewise for the opposite direction. Remember, differential steering, the only way I can steer is to slow down one wheel or stop it, or the other wheel to make it go left or right. So by calculating the new speeds, we can perform our steering, and this method here will set the speed for the motor, and it'll take into account the decel rate, assuming that it is active. Otherwise, decel rate is just simply 1. Then we're going to call out in the motor control method to go through, adjust the run velocity, and it will steer. At this point, we're just backing up a few inches so that we can read the QR code. That's the purpose of this function. My debug statements. Now we'll get into the decision-making portion of this method to see if it's completed its task. We're going to do an estimated calculation on distance to go based on where it is and then the average distance, or I'm sorry, not where it is, where it needs to be, and the average distance traveled for both wheels. If it's less than 0, that means I've gone past the destination. Usually this will trigger within about 0.25 millimeters or about 0.01 inches, 10,000ths of an inch. So it's actually quite accurate, just letting it flag that way. We'll stop the motors if it is. I'm going to take the current action from being perform check address to just 3 hyphen marks. That way nothing else gets activated. I'm going to update the home X and Y and home number data, home number being the road, and the home X and Y coming from the QR code as well as global X and global Y. If I'm debugging, I'm going to print that. I'm currently always printing this because I need a flag to make sure I do see the QR codes. So that's still testing, and we'll talk more about that in our next episode. And then finally, if there's still more instructions on the trip instruction list, this is the Python list that contains the whole trip instruction list, or all the trip instructions. If that's greater than 0, we're going to have to execute the next one. Finally, if we're looking at the distance to go, and if it's less than the distance to decelerate, we'll turn on our decel flag and start to slow down up here. That's it. All of the functions work exactly the same way. Now, as you can see, a lot of these are all the same. It's just what I need to check for during the motion, whether it's a 0 set and a tape marker, the preset magnet and a tape marker, or the QR code. How I have to steer. Am I steering using bang bang when going in reverse, or am I steering using line following with the analog inputs going forward? This helped immensely with getting a lot of my positioning errors and movement errors resolved, because I tried to do all of that in kind of one big function, and it was a mess. So at this point, I'm really thrilled with knuckling under, if you will, as the old saying goes, and just doing the rewrite and going with classes, because it did definitely make a huge improvement in code management, as it's intended to do. Finally, we get to the end of that, and then PTI says process trip instructions. So that would be what would happen when this method is, or class is all established. It'll run the first instruction, which is most likely nothing at startup. We'll look at a little bit more code, and then I'll just voice over some of the test data that I recorded, or test videos. So how does this whole thing run? We're down here already at the bottom of the program, and these are all the test commands that I just hand-coded and creating trip instructions. So in this case, these lines here would be sent from the scheduler to go through and do the check address, this line. Then it will add instructions, this command line, to the instruction list. Then it will dwell, because I don't want it to just jerk forward and backward. I give it I think a second or a half a second of dwell in between that. Then I will send the instruction to return, and then after it returns, it will dwell again. So that is what is required to perform that motion, all these lines. It's more data I'm transmitting and a little more handling I'm doing eventually over at the scheduler, but boy, it sure makes this program a whole lot more modular and gives me a lot more individual control for each motion. So as the program starts up right now, of course, it's going to read this. This is all main inline code. These are all additional commands that will be running, and I'll be talking over the video of them as they're being performed, because they're all pretty well tested now, and this is kind of my last check before going on to the next thing. We get to the bottom of that, we'll execute the trip instruction list, so it'll run the first command, which should be, you go all the way back to the top, that would be BEG right here. Come all the way back down, and then this is printing out memory stats like I've been doing all along. In our main loop, how does this all work? Well, that's going to get things started, and then things will start rolling along. But that's for just getting the start methods to define things. In our main loop, this is very much like it was in the past, but we're updating position data, doing our telemetry, checking our sensors, looking for a QR code. All that's happening every time through the loop, or we might skip. Like QR code, I'm skipping about every 9 loops, so 6 times 9 is how frequently I go through and check that. But here I do the PTI, process trip instructions, and then call this function process actions. So we will go find that guy up above, and that's up in here within the class, and that'll say which one were we using? Check address. So it'll say, okay, current action is perform check address, and we will go there, scroll down, and perform park. I think it's this one right here. And then this function would perform. So the mechanism to get it to run is quite a bit different than what we were doing in the previous version as well. So there are a lot of changes and differences in here, but in the end, frankly, I like them all a lot better now than I did in the previous version. There is one more thing, how I iterate through the list. That's kind of different. All right, when we call the executor method, which will do at the start of each trip instruction command. As we see here, we're going to see the pivot turn. That was from the command line, etc. I've got a list. It could be 100 trip instructions or 150, 200. I don't know. It'll be a lot of them. But I take a local variable and I say self, meaning within this class, TIL, that's the list containing the trip instructions, and I pop it. When I do that, that one goes into the run me, and then this one gets deleted out of the list automatically. So I don't have to manage that, deleting out elements and all that. Pop's kind of a cool little feature, and I think it's a little more elegant than doing it the way I was doing it in the last one. But that's how we iterate through the whole trip list. So with that, I will get things set up, and we will be filming these different motions, and I'll do some explanation of what we're seeing in the videos as they're being performed. Many of them are automated, where it'll run 5, 6, 7 times or whatever. Some I've got to manually position the Zoomie to repeat the maneuver. But my objective here at this point, everything's tested, so we should be able to see what the real world will be like with very little exception. Okay, here we're doing the check address and then the return maneuver. You'll see that the tail end wiggles a little bit, and that is pretty much the amount of gap between where the sensors see the white line and the actual sensors themselves. Otherwise, it's performing pretty good. In this example, we're watching the park and unpark maneuver without the rear encoder steering. Actually, I think it was implemented but not tuned up correctly yet so that we would get straight maneuvers. But this is the type of issues that have been plaguing the project since the beginning. We'll show you what worked better here in a moment after I made some changes. Here you'll see the Zoomie pulling in and into the driveway and then backing back out. This is the longest trip it would do. And you'll see that the tail wags a little bit as it's going across all the different color marker tapes. But nonetheless, it sure stays nice and straight all the way in and all the way out. And that will get us positioned for our pivot turns when we're backing out, and it will also get us perfectly positioned in the center of the driveway and over the little black marker tape, so we're at the right position every time. This test is the pull-up maneuver, and it just simply drives along the line to prepare for a pivot turn, either left or right onto the next road. I don't have a way to back it up automatically, so I'm just running it one time after the other, and then hand positioning it where it needs to be. This maneuver is using all encoder positioning feedback. There is nothing beyond that for it to determine how far to move and where to stop. Pivot turns were working pretty good in the previous version, both forward and reverse, but it's since gotten a little better control, and I'm much happier with the current results. You'll see it in this case go pivot turn in one direction and then in reverse, and it's going to repeat that, and we'll see it drift a little bit with each iteration, but it's really not that bad. Now that was left turns. We'll take a look at it doing pivot turns right, both in forward and reverse. Not much different here. Performance is about the same. Getting around the large sweeping turn was one of the easier of the two. The biggest issue had to be on the smaller one was getting the Zoomie lined up to read the QR code. We'll see that in the next set of test runs, but here you'll see I'm starting at pretty much at the exact right point where it would normally stop on the previous line, and it'll go around the corner, hit that angled marker tape, it'll slow down there, and then it'll hit our zero position or zero set marker tape and magnet, and it'll stop precisely. Now at this point you're going to see also that I'm starting it at different locations. The important part is if it stops at the correct destination. And what you really can't see here is I've actually got a mark on the guideline. You can see it there now, the pencil mark. So I know whether it's overshooting or undershooting. But that particular start is probably 1 inch off, and it still goes to the same place. On this smaller radius, it's 2.5 millimeter radius, I believe. So that would be about 65 millimeters radius. It will, of course, do the same thing. It's going to go all the way around the corner, decelerate at the first marker tape, and then continue until it hits the zero set marker, which you can see with the tape and with the magnet underneath it. Again, I'll change it to different starting points to make sure that regardless of where it ends the previous motion, at the start of the sweep turn, it will end at the correct motion, or at the correct position, rather. And these are all the problems that had to be dealt with where I didn't have as good a reliability as I'm getting now in this new version that's been a complete rewrite. The cruising test is a really important one because when we're traveling along a road, we're ultimately trying to get lined up to pull into a driveway or to turn onto another road. If our positioning isn't accurate along this distance, we're going to run into a lot of trouble. Now what I'm pointing out here is the relative location of two marker tapes. That's what it's programmed as. The one on the left right now, that's where it should be starting from. And then the one on the right, the yellow tape, is where it should be stopping. There is a QR code in between these 2 points, but you'll see how effective this is as we get through some of the tests. Here we'll start out about 1.5 inches, which would be 33 millimeters forward of where we started the last time. We'll see how this lines up at the end. Spot on. So even a full inch error, it's still doing really well. At this point, I'm probably 6 inches or 150 millimeters forward of where it thinks it is when it starts the move. Sees the QR code, updates the position, and we are spot on with the destination. Again, I got to give a shout out to Steve Woodgate for suggesting that idea. It is proving to be so awesome with this whole project. And frankly, I think without it, I probably would not be able to move forward. So kudos to you, Steve. Good job on a great suggestion. The motions are working a lot better in this version of the Zoomie control program. I'm really happy with how everything is working and behaving, how I can go in and tweak the code to adjust the behaviors ever so slightly to get better performance out of it. So again, for those of you OOP programmers out there, you're right, as always. I just got to quit being so stubborn and fighting that urge to not use object-oriented programming. This will pretty much wrap up this episode. We validated that the motions are pretty good. good enough to move forward, but the next important aspect is, can the scheduler track the Zoomie based on the Zoomie's feedback information? And that is the subject of the next episode. Hopefully that all goes well and we can keep marching forward. Thanks again for watching. I look forward to seeing you in the next episode.